Hello, this video is part of Unit 7 Biomechanics and looks at friction. Friction is in the forces assignment, which is 7.2. So first of all, the spec requires us to understand definition of what friction force is, different types of friction, a little bit of maths in terms of the coefficient of friction, and how we within sport and exercise science might use or try to reduce friction force. So let's first of all look at what friction is. It's defined as a force that resists the motion between two surfaces that are in contact with each other. So generally, if an object is in motion in one direction, friction force will resist that motion and try to effectively kind of slow it down in the opposite direction. So it's against the direction of travel, in the opposite direction. These friction force works parallel to the contact surfaces, so you can kind of see in both of these examples on the right, the motion is going left to right, and the friction force is parallel to that, working right to left, and that's true of the ball. The ball would slide along the ground there, but because of friction, for pushing the bottom contact part of the ball to our left, it causes rolling. So it's a parallel force to the direction of motion. Now, in your assessment, obviously, you need to use a variety of different examples of where we try to optimize friction. And in some cases, we try to increase it, and in some cases, we try to decrease it. Even a grip on many of the rackets or bats that we play sport with, we have a grip literally to optimize or, in most cases, increase friction. So let's look at a few other examples. So these sort of winter sports are often about going quickly over icy or snowy surfaces, and the type of material that's used, so in this case a steel or a metal runner, which is actually very small and thin, so small contact surface with the ice or the ground, is designed to reduce friction. You could actually argue that their clothing, their headwear, all of this is about allowing the air to slide past the body and reduce any surface friction of the air in contact with the athlete. The bikes that we ride, we've got, on the right hand side, probably something looking a bit more like a mountain bike tyre with quite deep, thick, wide tread. And on the left, a commuter bike or, a road bike would be a very thin, as in a narrow tyre or wheel with very smooth tread to minimize the amount of contact. On the right with the mountain bike, we might be going off-road, we might be going on different terrains, it might be rough or bobbly, and we want to get grip. On the left, the road bike, we want minimal friction so that we travel fast. Sometimes swimsuits, swimwear is designed to reduce surface friction. So we want the water, this liquid, to slide past the swimmer and have as little friction as possible, because that ultimately will slow the swimmer down. If they're not wearing an all-in-one like this, they might shave their arms and legs similarly to reduce friction. Surfer, so you can see the surfer here applying a sticky wax to the top of the surfboard. Now we've got, the board is obviously going to be in the water. The water will sort of go over the surface of the board and will act as a lubricant and make it even more slippery. But the guy surfing in this scenario obviously wants to be able to keep his feet in contact with the top of the surfboard so that he stays on it, and the wax acts as increase of friction. Conversely, the bottom of the board remains smooth because we want little to no friction on the bottom so that the board and the surfer slide across the top of the water without any resistance if possible. That would be true also of skis. So before you go skiing, on the bottom of the skis, they put wax and then make it smooth. I know it doesn't look like it there, but ultimately they will heat up the wax and make it as smooth as possible so that the skis glide right over the snow and obviously you travel as quick as possible. Footwear is another very easy way of considering friction and grip. On the left, we've got a range of different kinds of footwear. We've got studs in varying degrees, left to right. with more rubber, flat soles, rubber soles. And obviously you would select the appropriate type of footwear for the surface you were playing on, where you need to gain friction or where you don't need as much friction if the sort of flatter, less studded soles. And on the right, we've got footwear for short distance sprinters, to the other extreme where we've got a long distance runner. The short distance sprinters would want the most friction and have the most spikes so that they can get the most grip on the floor, on the track. Several sports, so gymnastics in particular, where there's grip, lots of events in gymnastics or weightlifting or climbing, all want to have as good a grip as possible between their hands and the equipment or the rock face. And so often powder is used to give a little bit of dryness because they might have nervous, sweaty hands, but also to gain friction, to give them grip. So let's move on to look at the different types of friction. The first type of friction is static friction. Now, this involves a level of friction between two objects so much that there is no motion. So static friction is when two objects push against each other in opposite directions and neither one moves. So this is static, means still. So the climber here has static friction between their fingers and the rock, or their shoe and the rock. In this tug of war, if we assume that there's no movement of this team, they have static friction between their footwear and the grass. So even if it's a split second, for example, hitting a ball with a hockey stick or a tennis racket, or even putting your foot on the ground when you're running, those sort of milliseconds, there is static friction. The contact surfaces are not sliding or rolling. Therefore, even for the tiniest moment, that is considered static friction. Without static friction, and if we were running, we would just slide like we were walking on ice. We would have no sort of purchase on the floor at all. So we must have static friction in order to move, run, hit objects. Conversely then, if we have two objects that slide over each other or move over each other, this is called kinetic friction. So for example, this stone in curling is sliding over the ice and there is a very small, negligible amount of friction opposing that sliding movement. If the opponent's tug of war team were pulling this team so hard that their feet were sliding left to right, there would be sliding friction acting in the opposite direction of that motion. And things like skates and skis, obviously travelling across or down the slope here, kinetic friction or sliding friction opposes that direction of motion. And again, on these two surfaces, it's probably very, very small. So kinetic friction occurs when a body or an object starts moving along a surface. So there needs to be motion for it to be kinetic friction, and it's also called sliding friction. So this is one example of sliding friction. I will talk about another in a moment. So if we've got, let's say, our tug of war team that were equally pulling against each other and there was static friction, their shoes were not moving at all, what we need is the other team to apply. So at that point, if there was no movement and there was static friction, the force that was being applied by the opponent's team at this point is too small because the static friction is keeping their footwear and the grass, the friction is enough between their feet and the grass to keep them still. If the opponent's team pulled a little bit harder, let's say this much, what we'd find is their feet would start to slip and there would therefore be motion. And therefore there would be sliding friction or kinetic friction between their feet and the grass as their feet slipped left to the right. So if a big enough external force is applied beyond this sort of level that we can overcome that static friction, then we start moving and there will be kinetic friction between the two surfaces. But we revisit this later. Just before we move on, actually, the point with which you reach that amount of external force is called the limiting friction. So beneath that level, there would be static friction. Above that level, there's motion, there's kinetic friction. Here's just another example of how we might experience kinetic friction as a training method. So some athletes will actively choose to create sliding friction between their feet and the surface, obviously choosing to run up dunes on sand. And this is so challenging for them because their feet literally just slide down each footstep through the sand, making it extra demanding for them as a training strategy. But this would be kinetic friction or sliding friction between their feet and the sand. So the third type of friction we need to understand is rolling friction. So rolling friction only relates to objects that are typically round, spherical, or cylindrical. Obviously, if this was a cube, it would not roll. So we want objects that are, rounded. So rolling friction is the force that slows down the motion of a rolling object. So the contact between the surface of this rolling wheel and the ground is where rolling friction would occur. And it probably would depend on the surface of this road, let's say, if it's a wheel, how much rolling friction there was. But the wheel is rotating this way. If it wasn't rolling, it would be sliding. There would be no rotation. It would just be sliding that way. But because there is friction between this wheel and the surface, the friction causes this roll and it continues to roll. So the amount of rolling friction would allow the ball to roll quickly and easily, or would slow it down even more. So if you imagine a golf ball rolling on the green, which is a really short cut area of grass, there's probably less rolling friction than if a ball was hit into the longer grass and was rolling. It would slow down much quicker. So the amount of rolling friction, as I said, is determined perhaps by the amount of contact surface or the type of surface, the characteristics of the surface. Is it smooth? Is it rough? Is it long grass? And if there's any lubricant, often water or other products on the surface that would make it more or less slippery. And a nice easy example of a combination of these types of friction is when we first hit a ball, for example, when we're putting. So once you make contact with the ball here, actually what it does initially is skid. So this is the ball sliding, not rolling. There's no rotation at this point. So that is sliding friction initially, or kinetic friction, as the spec calls it. But actually after a moment, the ball would gain so much contact friction down here that rolling would occur. So the amount of friction here increases, causing the ball to roll as we would probably understand it to. But that's quite a nice example to combine a couple of different types of friction. Of course, before the ball was hit, there would be static friction between the ball and the grass, so you could argue there's a third type there. The last type of friction actually is another kind of sliding friction, but I've just differentiating this one rather than two surfaces in contact with each other. This is now an object in contact with a fluid. And what we need to understand, and hopefully is represented by the examples there, is that a fluid is either liquid, often water, or gases, for example, air. So there would be fluid friction or sliding friction or surface friction between this object and the air that it's passing through, or this object and the liquid that it's passing through. So third friction is resistance to motion of an object or liquid body in a fluid due to friction exerted between the body and the fluid. So just to pull those types of friction together before we move on, here's some examples. So we've got rolling friction, static friction between the feet. We've got static friction between the tee and the ball. We've got static friction between the grass and the ball. We've got fluid friction if the ball was flying through the air, as it just about is, but also it would be fluid friction in the liquid of the water. We've got sliding friction or kinetic friction as the ball slides through the grass. You could argue it would be fluid friction as the ball goes into the air also maybe. And then as we know already, we would have kinetic or sliding friction initially, and then rolling friction as the ball travels along the green. So the slightly more involved topic within friction is called the coefficient of friction. Now, before we kind of get into the maths that's involved in the coefficient of friction, let's try and look at things that influence how much friction there is. So Linthorne and Cooper did a study, and they looked at doing a 30-meter sprint pushing this sled. But they varied how much weight, so in newtons down here is how much weight was on the sled, not very much to loads. And they varied the surface that the sled was pushed over, from Astro for a hockey pitch, 3D football pitch, a grass rugby pitch, or a sort of athletics track, which is quite a rubbery surface. And hopefully you can interpret the graph and notice that in all cases, when there was less weight on the sled, there was less friction force between the two surfaces. Where there was most weight, there was the highest values for each of those 4 different surfaces. So the first point to recognise is that the larger the mass of an object, the greater frictional force there's going to be between it and the other surface. The second thing is, it's not just how much weight the object has, it's what type of surfaces are sliding past each other. So the sled is obviously a constant type or characteristic, but we can see obviously that these 4 surfaces are very, very different. Notably, there was less friction in all cases between the Astro hockey pitch and the sled. So there was less sliding friction between that surface and the sled compared to the athletic track, which, as we know, was a bit more rubbery, which kind of makes sense. The values were highest. So a rubbery surface and the sled has a higher coefficient of friction and therefore would have the slowest times. It was harder for the athletes to push this sled across the athletics track surface than it was on the slippery, slidey, low coefficient of friction artificial grass pitch. Which sort of makes sense. So what I'm getting at is the coefficient of friction is a value that represents the level of slidiness, slipperiness, ease with which the surfaces slide over each other between 2 surfaces, and any 2 surfaces. So unfortunately, this again is some data from the same study. It doesn't give us actual numerical coefficients of friction, but it just indicates which ones have lower or higher coefficient of friction. Lower meaning they slip between each other, the sliding friction, the kinetic friction is low. So steel and ice, obviously those are 2 events where we don't want friction. We want the skates to move easily over the surface, the ice surface. Another ones that are low are beach handball, where we have bare feet and sand, again slippery, and clay tennis courts with the footwear, rubbery footwear. And those are designed by design are quite slidey. The techniques involve sliding across the court to stop yourself. The other ones all have much higher coefficient of friction. And obviously these are traditional rubber and grass, rubber and hard surface. So the footwear with the performance surface gives us a bit more friction. So let's just try and get our head around what is the coefficient of friction. It's a measure of the amount of friction between 2 surfaces, 2 bodies, 2 objects. And it's represented by this mu symbol, this funny looking U. It doesn't have a unit, so whatever value the coefficient is, it doesn't have a value other than it will be between 0 and 1. And 0 means there is no friction between those 2 surfaces. They are so smooth, there's no friction at all. 1 meaning there's so much friction that the objects will be static. There's no slide. So if there's a coefficient of friction, it's a highly static or highly sticky surface. In the equation, so we would use this equation to calculate how much friction force there was between the 2 surfaces. We need the coefficient to specify what the characteristics of the 2 surfaces are, but we also need to use in the calculation normal force. And this is pretty straightforward because normal force is just the same as weight. So we know already that weight is mass times gravity. So the mass of the object times 9.81 newtons. So we would do that to calculate normal force. we would need to know the coefficient of friction. We times those two together, and we then know how much friction force there is. Probably easiest if we have an example. So here's Ronaldo sliding to celebrate a goal, and we've got kinetic friction slowing him down as he slides. So we want to know how much friction there is between his knee and the grass. So the coefficient of friction for sliding on grass is 0.53, so mid-range. Remember, it's going to be between 0 and 1. We need to calculate what normal force is, so mass times gravity. Ronaldo's mass is 83 kilograms. Let's, for simplicity, round gravity up to 10, so we times those two together and get 830 newtons. So we now need to go 830 newtons times the coefficient of friction, which is 0.53, gives us a friction force of 439.9 newtons going on between those two surfaces as he slides, and it's that simple. Just to give some examples and context for how sliding, what the coefficient of friction is and how it influences us, there have been other studies that look at this. So this is different tennis court surfaces. And what they showed is that the surfaces that had the lowest coefficient of friction, i.e. were more slidey and slippery, like clay, had the lowest risk of injury. If you think about it, playing on hard surfaces, you get a lot of grip between your footwear and the surface. And if you're sprinting a very short distance, abruptly turning, you're more likely to perhaps have ankle and knee injuries rather than if you slide to slow yourself down. And it's a bit almost, it might look out of control, but it's probably a bit easier on your joints and limbs as you do that. Now, what I've been able to find is a couple of examples of coefficients of friction. I couldn't find lots. So we've seen the sliding on grass one with Ronaldo. This one is for sliding on clay, so rubber tennis shoes and clay courts, and the coefficient is 0.43. And all you need to do is put your mass or a chosen mass in there and do the sums exactly the same as we did with Ronaldo. So that's a slightly lower coefficient of friction. A running track, so I found it was between the footwear and the track is 0.85, so there's greater coefficient of friction, which makes sense because we want good grip on the track to be able to propel us forwards. So again, exactly the same, put a chosen mass value in there. What it might be a good idea to do in your assessment is to pick two examples of contrasting coefficients. This is a really high one, pick one that's really low. Here's what, this is a football boots on grass. 0.35, different value again, of course. Put your values in there for maths. I just want to revisit the scenario where we've got static friction, where an object is still, and then we overcome that by an external force causing kinetic friction. So the sled was still, this athlete's got to generate a big force to start it sliding. And once it's got it sliding, it's actually a bit easier for them. So they have to get a big force to get it going, and then the force they need to keep it moving is less. And the same would apply to these sort of scrum machine type things. You know, they push here. To get it going is harder. Once it's going, it's a bit easier. So just remembering the graph that I presented a little bit earlier, if we were looking at the sled, the athlete would have to apply a big enough force to sort of overcome that static friction and get it moving. And the amount of force, the amount of force that's needed here is key, because once they get the sled moving, or once they get the scrum machine moving, the amount of force they need is less. So limiting friction relates to the force that is required to exceed the coefficient of static friction to get the object moving. So there's an amount of friction between two surfaces, and up to that point, you won't budge the object. Above that point, you can make it move. So you need to apply a bigger force than that limiting friction in order to cause motion of an object. And then once you've got it going, the amount of force you need to keep it moving is typically up to about 25% less. So you can see the amount of friction force here is much less. So kinetic friction values or kinetic friction coefficients are always lower once things get moving, it's always a bit easier. So I struggled to find too much in terms of sports examples, but this is something just to show really that all the static friction values between these two types of surface are higher than the kinetic friction values. So rubber and dry concrete, so road running with trainers on the concrete, the static friction value coefficient is higher and the kinetic friction value is lower. Steel and ice, so that's our ice skating one, the static friction value is higher, the kinetic friction value is a lot lower, just to make the point. So the last little bit we need to look at is things that influence how slippery, slidey surfaces are, that in terms of what the coefficient of friction is. This could be a nice one to use in terms of ice skating, actually, for your calculation example, because this is the coefficient of friction between a speed skating blade and ice. And these are designed very specifically to have the lowest kinetic friction, so sliding friction, as possible, because obviously they want to go as fast as they can. They don't want to be slowed down by the contact of the blade, and that's a really, really, really low value. Remember, it's between 0 and 1. But obviously what they've also got to do when they're skating is they've got to propel themselves forward. If they just had their blades forwards and moving, sort of sliding forwards and backwards, they wouldn't go anywhere. It would literally just be sliding their feet forwards and backwards in a stationary position. So what they do is they turn their blades diagonally sort of to the side and push against it. You can sort of see the angle of the blade here, and create static friction. So in that moment where the blade's turned a bit sideways, they push off the ice, they dig their blade in a bit, they create static friction, which then propels them forward. So speed skating is a mixture between static friction every time they take a stride to push themselves, and sliding friction or kinetic friction when they're just motoring along and literally sliding on the blade. Quite a nice sort of different example, again blending a couple of different types of technique. The surface characteristics of the surfaces obviously will influence how much friction there is between the two surfaces. Your choice of footwear: if you played on a grass pitch and wore football boots with studs, there'd be a higher coefficient of friction, you'd have better grip than if you wore your trainers on, let's say, wet slippery grass. You'd have much less friction, there would be a lower coefficient of friction. We choose our footwear often to suit the surfaces to get optimal grip. There's a video here, I'm not going to play it in this instance, but it just illustrates that the grooves in this kind of wedge shot are essential for creating friction, allowing friction between the golf ball and the face of the club. When you hit a golf ball, quite often you get grass and water trapped between the ball and the surface of the club. And these little grooves just provide an opportunity for that mush of grass and water to shoot out the side, keeping this surface clear so that the ball can make good contact with it, because the ball, without some friction, would just slide. The ball is here, the ball would just slide off the club. And what we want is for the club to hit the ball and to create backspin. And you can't do that without some friction between those two surfaces. So it's a really clever design to optimize friction between the golf ball and the club surface. Sometimes lubricants are present between surfaces. That means probably liquids or dust, you could say. In these cases, the floors being wiped, the surfaces are being cleaned so that there is optimal friction between the footwear of these basketball players. I think it's a tennis court, is it? Or a badminton, actually it's probably a badminton court, because they want to have grip. If sweat has dripped on the floor, that will act as a lubricant and they will lose their grip and obviously possibly damage themselves. So in these cases, we don't want lubricants involved between the surfaces because it is problematic or has safety implications, nor do we really when we're cycling or in F1 cars like this. and they would change their tyres. You can see that they're actually quite grippy, these tyres, because the conditions are so bad, and the water and the rain acts as a lubricant and makes it more slippery, reduces the coefficient of friction, which isn't ideal. If you see those tyres and the surface is dry and warm, they'd be really smooth. They don't need this level of grip on the tyres. Here's an example where we actually actively choose to lubricate the sort of mechanisms on a bike, on a chain, and the cogs, because we want them to we want to have no friction or less friction so that they smoothly work over each other and don't wear, and obviously function well. So some sports we use lubricants actively, and several sports we want to try to minimize lubricants interfering with performance and friction. So another thing that can affect the amount of friction between two surfaces is how much contact area there is. Where there's more surface area in contact with each other, there's going to be more friction. Where there's less, there's going to be less friction. So if it's quite a bobbly surface, you're not going to get as much grip, you're going to have less friction than if there was a lot of contact with the two surfaces. And that's actually true of curling. So they spray the surface of these sort of curling rinks, which the spray makes the ice, when the water freezes from the spray, it makes it quite bobbly, which reduces the amount of contact surface between the stone, the bottom of the stone, and obviously the bobbly surface, which makes it run true and reduces friction. And the other thing they do is they do slightly warm the surface to make it smooth as well, so that the temperature change affects that also. So just to summarize, there are lots of things that can influence the level of friction between two surfaces, and we've looked at quite a few of them in the examples I've gone through. This really just summarizes all the different things that can influence the coefficient of friction. So just to finish up, that's the spec again. We've been through all of those things. Hope that makes sense.